On page 346, they describe all of the transformations that you could have and what they would do. And they say, as a result, your general form is x over d plus h, comma, cy plus k. Now, if we go back to chapter 3, you could remember this, not very easily, I don't think. Or you could just do what we've done every time we did things in chapter 3, which was we just work from left to right. And a little reminder, you take points that were on your graph. Do you remember doing this? And we always did our stretches and reflections first, followed by all of our translations after that. So we did our stretches, reflections first, and our translations. And if you just went from left to right, that's naturally how those numbers would hit. Your first numbers that you would hit were your stretches and compressions, and then your next numbers were all your translations. Which is a lot easier, unless this word makes like x, if that's really easy to remember for you, then go for it. Right? But if not, left to right might be easier. So we're going to do an example here first. You can do it right underneath this. We're going to graph y equals negative 5, 3 to the power 2, bracket x plus 4 minus 7. And part of the reason these ones weren't in chapter 3 is it makes sense for us to be able to review things now. And another reason is they're a little bit trickier because you might be tempted to do things because the parent graph has a number in it. So first of all, we have to look at all of this, and we have to decide, what's our parent graph? Y equals what? 3 to the x. So you have to recognize that that's your parent graph, and off to the side, I like to always sort of like quickly do a quick sketch. What does that parent graph look like? It looks like this. It has an asymptote at y equals 0. I know that the points, it goes through 0, 1, and the other key point is 1, 3. And now the important thing about the parent graph is then when we go back to our equation, we need to recognize that this is our parent graph, 3 to the x. And that 3 doesn't affect your transformations. The most tempting thing you're going to want to do with this question is your whole body's going to see negative 5 times 3. You're going to want negative 15. I know my times table. I'm good at that. You're going to want to multiply that 5 times that 3 right away because it's the first thing you see. And it's so tempting to want to do that. Now, you learned way back, I don't know, when did you learn bed mass, order of operations? Is that grade 7, grade 8, grade 7, order of operations? Now, there's an order of operations that says exponents comes before multiplying. And if you multiplied this 5 times 3, you would be multiplying before you did 3 to whatever that exponent is. We can't actually multiply that exponent out because it has an x in it. So you're like, oh, well, then maybe I should multiply the 3 times the 5. No, because then you're going against order of operations. So that's the first thing that makes these a little bit more difficult, is they're going to be tempting you to do things out of order. You can't multiply that negative 5 times that 3. The other thing is you might be tempted to put that 3 in as one of your stretches or compressions because you see a number. And all of our questions up till now, anytime there were numbers, those were part of our stretches and compressions, and anytime there were other stuff, that was just part of our parent graph. Well, this one has a number in our parent graph. So we have to go from left to right, we have to take our points, but that 3 doesn't affect your transformations. That 3 is part of our parent graph. So what we're going to do is we're going to take our points that we have on our graph, which are 0, 1, and 1, 3. We're also at the end going to look at what happens to our asymptote y equals 0. So 0, 1, going from left to right. The first set of arrows was always our stretches and compressions. So going from left to right, we have a -5. That's going to be a vertical reflection and a vertical stretch. What is that y equals -5 going to do? It's going to multiply your y values by -5. Exactly the same number. Going from left to right, the next stretch or compression you hit is the 2. And here, I'm going to highlight whatever is where the x value is. In other words, whatever's in the exponent, that's all horizontal translations and transformations, stretches and compressions. So what happens if that 2 is inside the exponent? What are we going to multiply our x value by? Do you remember? How do we do horizontal stretches and compressions? Would you multiply x by 2? No. Everything that was horizontal was kind of the opposite, right? So instead of multiplying x by 2, we multiplied it by a half. And so we can take our points. What's going to happen in 0, 1? It's going to change to 0, -5. What's going to happen in 1, 3? X by a half, y by -5. Next set of arrows are translations. We have a +4. Okay? In the highlighted part, we have a horizontal stretch and, we have a horizontal compression and a horizontal translation. We had that special note that says it needs to be in factored form. This one nicely is. So we don't have to worry about it, but it's still good to think about that. So with that 4 is going to mean that we're going to go 4 to the left. And the -7, that's telling us that we're going to go 7 down. So now we can take our point, 4 to the left, 7 down, 4 to the left, 7 down. And the only thing that's going to affect your asymptote, which is on your x-axis, is whether your graph is shifted up or down. In this case, our graph is going to be shifted down 7. So our asymptote is going to change to y equals -7. As a result, what does our graph look like? I'm going to start by drawing my asymptote at y equals -7. I'm going to label my points 4, -12, -4, 1, 2, 3, 4, -12. And -3.5, -22. Estimate where that'll be. And that's supposed to be enough information for us to graph our exponential function. So here, we have to know some things about exponential functions. We know their general shape, that they approach that asymptote. So based on where my points are, for sure, the values are going to be connected between these two. Can you see if these two are connected, I'm going towards the left, that would mean it approaches my asymptote in this direction. And it would keep on going down in this direction. So for our final graph, we need to label 2 points on the graph. And those we can find by doing our transformations from those 2 key points on our original graph. We need to label our asymptote. We need to have the shape, the general shape, be the same as the general shape of an exponential function. And this is what our graph is going to look like. So now for example 2, They're telling us what the parent graph is. It's 2 to the x. And we want to graph y equals 3, 2 to the negative x plus 2. First of all, I'm going to notice that I have a horizontal reflection and a horizontal translation. And it's not in factored form. So my very first step is I'm going to factor out the negative, leaving me with x minus 2. Off to the side here, I'm quickly just going to draw a sketch of y equals 2 to the x and label those key points, because those are the points and the asymptote that I'm going to use to figure out my graph. Again, I don't know if you want to use a highlighter or a pen. Our original graph is y equals 2 to the x. So that means that this and that 2 are not part of our transformations. And we're not going to multiply the 3 times the 2 and get 6, because that would go outside of our order of operations. Anything that's not highlighted, those are going to be transformations that we're going to do. So when we set up our points, we have the points 0, 1, 1, 2, and our asymptote at y equals 0. Going from left to right, doing all of our stretches and compressions first. We hit the 3. What is that 3 going to do? It's going to multiply our y values by 3. Then we hit the negative sign. So notice that, nice that I've highlighted the 2, that I don't have to think that that 2 is part of a stretch or compression. The next thing I hit is the negative. That is a horizontal reflection. That'll multiply your x values by negative 1. Finally, you hit the minus 2. It's inside the function. That will move it 2 to the right. So now we can just fill in our values. This will become 0, 3. This will be negative 1, 6. Go to the right 2, 2, 3, 1, 6. The only thing that's going to affect your horizontal asymptote is if your graph is shifted up or down. And in this case, there's no translation up or down, so our asymptote stays at y equals 0. So when we go to graph, our final graph, I always like to start with my asymptote at y equals 0. Plug in our points. We've got the point 2, 3, and we have the point 1, 6. So with those 2 points and our asymptote and knowing the general shape towards our asymptote, make sure you add arrowheads on both ends to show that it increases and goes up forever. So is this one increasing or decreasing? This function's decreasing. If I wanted to find an intercept, well, there's no x-intercepts because I have an asymptote at y equals 0. If I want to find a y-intercept, which isn't graphed, how do you find a y-intercept? Plug in 0 for x. So let's go to our equation. What would happen if you plugged in 0 for x? You'd have 0 minus 2 times a negative, be positive 2, 2 to the power 2, would be 4, 4 times 3. You'd get the point 0, 12. Equation of the asymptote we already have, and I'll do domain and range here. The domain is everything. Your range is bigger than 0. Now the questions we're going to do from the homework are 10 and 13, but we're going to do one more set of examples before we go to that. I believe you have a blank page on page 357. So we'll do two graphs on this graph. The first graph that we're going to do, so I'm going to introduce you to a new number. The number e. So anyone ever seen Sesame Street? Was that still on when you were a kid, or is that no longer a show that was on? No. Sesame Street was a kids show, and every kids show they would say, and today's program is brought to you by the number 3 and the letter L. And whatever reason, they just, instead of brought to you by advertisements, I don't know, but that's what they did. But they never had a show where it was brought to you by the number E. Have you ever heard of the number E? You've probably heard of the letter E, but have you heard of the number E? Some of you maybe. Can you find it on your calculator? Can you tell me what E is equal to? E is a weird number. It's like pi. Pi is a number. You know that one's 3.14. E is a number. Can you find it on your calculator? Enter it in, push enter, and see what it tells you. So yeah, you found it? Anybody else found it? It's not 0. You have to, it'll actually not the letter E, the green ones are letters, but you have to find the number E. 2.71, like if you, now, it seems to tell you on your calculator like, oh, that's a cool pattern. Does it keep doing that? The answer is no. It looks like it just go 1828, 1828 forever, but it doesn't. It does that just for the beginning, and then it goes crazy, and it follows no pattern, just like pi has no pattern after that. So it's a weird number, but you can graph it. You can graph any number that's a base. It's exactly the same as graphing 2 to the x. It's exactly the same as graphing 3 to the x. You're going to have an asymptote. Where do all of our asymptotes on our exponential functions have asymptotes? At y equals 0. What point does every single exponential function have? 0, 1. And on this graph, you're going to label 1, 2.718281828, but instead of writing all of that, you're just going to go 1, e, and estimate where 2.7 is. So here's 1, 2, 3. I'm estimating that that was 2.7. And draw your exponential graph. The number e. Okay. So if you could graph this is the parent graph for the number e. So now that you can graph the parent graph for the number e, in number 2, you will also be asked, because the number e is very important in calculus and in population growth problems and a lot of mathematics, and it is also very important in logarithms, so it comes up a fair bit in this unit. So we'll be asked to graph exponential functions with a base of e, and we'll be asked to graph exponential functions with transformations with the base of e. So just like all of our other exponential functions, it's not any more difficult. The process is the same. The numbers just are weird because we're dealing with the number e. So again, just like before, I might take out my highlighter and say that e and that x, that's part of my parent graph. And then I'm going to look at, well, I have the point 0, 1. I have the point 1, e. going from left to right, dealing with all of my stretches and compressions first. So from left to right, I hit the 3. What's that going to do? That's going to multiply y values by 3. Next, I hit the +2. That's going to go to the left 2. And finally, I hit the -5. That's going to make it go down 5. So what happens when you multiply by 3? Well, you get 0, 3, and 1, 3. 3. 3e. There we go. And after that, left 2, well, that'll change this to -2. And down 5, that'll change that also to -2. Left 2, -1. And what do we do when we want to go down 5 from 3e? We just write 3e minus 5. And that would be an exact value. So we try to leave things as exact values. When we go to graph this, oh, we should also talk about our asymptote. The only thing that's going to affect a horizontal asymptote is whether things are moved up or down. This is moved down 5, so it changes to y equals -5. So I would start by drawing my asymptote. Next, I would probably label the easy point, -2, -2. And then to figure out what 3e minus 5 would be, okay, you're going to use 2.7 as a rough estimate for e. 3 times 2.7 is about 8.1. 8.1 minus 5 would be about 3.1. So I'm going to go up to 3. I'm going to label -1. I'm still going to keep it as 3e minus 5 and have that second point. And now that you've had 2 points, your exponential function would have to decrease that way, increase that way, and so we have our final graph. So again, if you didn't write them down from before, to practice graphing, questions 10 and 13.